This is a frame, and it's making an angle of 20 degrees, and there is a roller support. And this being, it's been hinged at D. So this is a question, and there is an 8 pound load that's at an angle of 20 degrees, and the 5 pound load here, and this is making an angle of 30 degrees. And the respective lengths are given. And what are the questions? For the body shown, find the reaction at A. How is that? Yeah, see, you can see this is a roller support. So, and we'll have only one reaction that is normal to the roller, correct?
Yes.
Let me call it as RA.
Yeah.
And also that's first question. And what's the next one? The find the reaction at D. And you can see we can, let me take moment about D. Okay. So take moment about D. Let me draw first the free body diagram of it, or no? If I draw the free body diagram, it looks something like this. This is that length. So we have RA here, and the 5 pound load, and an 8 pound load, and we can have two
So in
reactions.
such questions, the first thing I should probably do is just draw the free body diagram to make more sense of it, right?
Yes. So if you draw the free body diagram, you'll get to know what is the right point about which you can take moment.
Okay.
And you can see here, we have and since D is a hinged support, we'll be having two reactions, right? One here like this. Let me call RDX and RDY. Okay, the two reactions at D.
So you just know that, right? Like that's one of the rules you just need to know. Like it has two supports. It has two forces acting on it.
Sorry.
It's just one of those.
No, it's a hinged support, right? It's a hinged support. Had D been a roller support, it would have only one reaction.
Okay.
It's an hinged support, correct? Because it will not let the frame move in this direction. It will not let the frame in this direction, correct? It will not let the frame move in both perpendicular directions. So that's why it will have two reactions, correct?
Okay. Wait, but then the roller support moves in the X direction as well, right?
But there is no one resisting it, right? It can move.
Yeah.
It can move freely, right? It can move freely up and down along the plane.
Yeah.
But it can't move freely. D can't move freely because it's been fixed.
Yeah.
That's the thing. So let me, and correct. And I can say I can take moment about point D. See, this is point D, correct? This is D. If I take moment about point D, what is the advantage of taking moment about point D? So if I take moment about point D, I can eliminate two of the forces at D, because when a force passes through a point, it can't create any moment, right?
Yeah.
So that's the advantage. And in the whole moment equation, I'll be having only one unknown, which is RA, right? With the help of that, I can solve for RA. So that's how we do it. So, and you can see how is that we, so first of all, what is that we have to do is we should be we should know this angle actually. So what RA is creating with respect to this. Let me call it as theta. If that is theta, so this will be RA cos theta, and this will be RA sin theta, right?
Yeah.
And what is What is the angle we can, I think we can calculate that angle. This is 20 degrees, right? So this is 20, and if that is 20, what are the other angles we can create? So this is 30, correct?
Sorry, which one is 30?
Uh,
Oh yeah, okay, that one. Yeah, got it, got
that's
it.
30. So
Yeah. Wait, so
we
would
can
theta
see
be 60 then?
this would be theta, this would be 60, right?
Yeah.
So if that is 60, and this would be 30, and if that is 30, what is that we can we comment on this?
On theta?
Yeah,
Um 30. Yeah, I
I
mean that whole thing needs to be 90 as well. And since other side, so theta needs to be 30 as well.
yeah, theta needs to be 30. Which whole
Yeah.
thing, this, which whole thing needs to be 90? This one.
Yeah, and the whole thing needs to be 90, right?
That's okay, that's 90, but um so
So
I
wouldn't
think
theta be 30?
no, theta won't be 30. How is that we got, how is that we got theta 30?
Oh, no, it wouldn't be. You're right. You're right.
It would have
Sorry.
been 30. It won't be
Yeah,
30.
yeah.
It would just,
Um,
so 1 second, let me, so this is, oh sorry, and you can see this is normal to this, okay? This would be 90, so this one would be 90.
yeah.
If that is 90, what are the angle that we can talk? Yeah, yes. Yeah, you can see one thing. Yeah, see this is the 20-degree angle, correct? And you can see this one is RA. This is RA, which is perpendicular to that frame, correct? With that line.
Mm.
Are you
Yep.
getting this? Yeah, this is
Yeah,
90,
I'm
correct?
getting.
Yeah. And
Yeah.
I can make a angle like this, correct?
Yeah.
Can you see that? Here, this one, this needs to be 90, and if this is 20, this needs to be 20, right? This should also be 20,
Yeah. Yeah. It has to
and
be 20.
if
Yep.
if this is 20, this needs to be 70,
Yeah. It
and
has to
if
be 90.
yeah,
Yeah.
if that is 70, and yeah, you can see if this is 70, this is 60, this is 30, and this whole angle needs to be 180, correct?
Oh, okay. Got it. Got it. Yep.
70, 70, 30, 70, 30, 100, 100 plus 60 is what? 160. This will be 20.
160. 20.
This would be
Yep. Yep.
okay. So
Yep.
that's 20. And so in that case, this will be RA cos 20, and this will be RA sin 20.
Yeah. Got it.
Okay. Now I can take moment about all the points. Okay. And you can see, let's take moment about and what would be this angle? Okay. The uh, if I take moment about, now let us come back to this thing,
Mm-hmm.
the free body diagram. This is RA, what's that? It's cos, right? It's RA cos 20 degrees, and this is RA sin 20 degrees. And what is the moment created by RA sin 20? RA sin 20 about D. It is this multiplied by this distance.
Yeah.
And what is the distance? So it will be this 6. This is given as 6 inch, correct?
Yep.
And this is also given as 6 inch,
You just need to find the horizontal
and
distance.
this is 30 degrees. So this length would be 6 inch, 6 sin 6 cos 30.
Yep.
So what the moment created by RA sin 20 would be, RA sin 20 is a force, and it is at a distance of 6 cos 20 plus 6, right?
Yep.
And now Now what would this distance be? This would be 6 sine 30.
6,
Correct.
yeah.
And what is sine 30? Sine 30 is half, right?
Yeah, got it.
If sine 30 is half, this should be 3 inch.
Yes.
And you can see this is also given as 3 inch.
Which one is, yeah, it is obviously.
That means RA cos 20 will be passing through D, right? If that is if see both are 3, both are at the same level, 3 inch
Yeah,
and
yeah,
so that means if RA cos 20 is also passing through D, then RA cos 20 can't create any moment, correct?
yeah.
So we can eliminate RA cos 20. Okay.
Wait, sorry, can you repeat that? Why it can't create any moment?
Yeah. For that I'll have to draw this again. So it is like this. Okay? This is the thing. This is the thing, and this is the frame, and this is RA cos 20, RA cos 20, and we just got to know that it is at a distance of 3 inch from this bottom line, correct?
Yeah,
And it's given that D is also 3 inch. So this DC thing.
yeah,
And if I extend this, what happens? Both are at 3 inch. It will just pass through D.
yeah.
If it passes through D, it can't create any moment, correct? For it to create moment, it should be at some distance from D,
Oh, okay.
correct?
Yeah,
So in that case, that won't create any moment. And the only thing that creates moment are these three forces. So RA sine 20 can create moment. This is a moment created by RA sine 20. RA sine 20 multiplied by 6 cos 20 plus 6. And that's the moment. And we just got to know RA cos 20. Since RA cos 20 passes through D, it can't create any moment. And let's talk about one more force. This 5 lb force can create moment, right?
yeah,
And what is the moment created by it? It's 5 lb into 6. 5 lbf into 6.
yeah, it is.
So let me take that also. 5 into 6 inch, right? 5 lbf into 6 inch. So that's a moment one. That's a moment created. And this 8 lb, that's there here. This can also create moment, correct?
Yeah, but only the vertical direction.
Yeah, exactly. Let me, if we can
Yeah,
split this into components, this would be 8 lbf cos 20, and this will be 8 lb4 sin 20. And this 8
and
lb4 lbf sin 20 can't create any moment because it simply passes through D again. And the only force that can create is 8 lbf cos 20, and it is at a
cos
distance
20,
of
yeah.
3 inch. Yeah, and it is at a distance of 3 inch from D. So what was the moment created by 8 lbf cos 20 multiplied by distance 3, right?
Yeah.
Now we'll have to talk of the sense of moments created. This RA sin 20, it is trying to rotate the frame in clockwise direction about D, right?
Oh, yeah.
Now,
Yep.
let me write that here, clockwise. And what is the sense of moment by this 8 lbf cos 23? It is trying to rotate the beam in anti-clockwise direction, correct?
Yeah, because only that force. Yeah, it is.
Yeah,
So it
it is.
cancels out. So it equals each other.
Yeah, it's anti-clockwise. And we have one more force, this 5 lb thing, and it is also trying to rotate the beam about D in anti-clockwise sense,
Okay, yeah.
correct?
Yeah.
Yeah, and we have one clockwise moment and two anti-clockwise moments, and their summation must be balanced, correct? The clockwise moment
Well,
must
the
be
5
balanced.
lbf is moving it. Yeah, it's moving it anti-clockwise. Yep.
Clockwise. So what are the anti-clockwise moments? 5 lbf into 6 plus 8 lbf cos 20 into 3. These are the anti-clockwise moments, and that must be balanced by the clockwise moment creating by RA sin 20. Got it?
1 second.
See, it's like this. The moments must be balanced, right? The clockwise moments and the anti-clockwise moment must be
So
balanced.
yeah, the anti-clockwise moment is equal to the clockwise moment, right? Like you see,
Yes.
equate
Yeah.
each other.
Yeah.
Okay.
So these will get added because they are in the same sense. both have got same sense. Correct. The 5 lb, the moment created by 5 lb force and the moment created by 8 lb force have the same sense. Correct. Both are
Yeah, yeah.
anti-clockwise. That's why I added them, and that must be equal to the clockwise moment. Only one force is creating clockwise moment, that is Ra sine 20. Correct.
Okay, yeah, one sec. So you do that, and then 5 lb
That
f.
should be what, 8 5 6 are 30 plus 8 3 are 24 cos 20 divided by sine 20 of 6 cos 20 plus 6, that must be equal to Ra. Correct.
Yeah,
So this is Ra. Sorry, shall I calculate it or
no, it's okay. You can move on. I can just do that myself.
uh, you just got to know the thing, right? How is that we calculate that?
Yeah, I understand how to do it. I understand how to do it.
Yeah, yeah. And shall we go? We have one more question here. The
Yeah,
reaction
we
at D.
do. We have to find reaction at D.
So that we can find using simply using the force balance, right? Correct. Let me draw the
Oh yeah, like summate all the forces in the x and y direction and then find it,
yeah,
right?
that's it you can
Okay.
find. In x
Yeah, that
direction
I
you will,
can find.
yeah, if you do the force balance in x direction you will get rdx, and if you do force balance in y direction you will get rdy. That's it.
Okay, and then you just magnitude that and then find the direction as well
Yeah,
from there.
yes, that's it.
How would you find the what is the direction, magnitude and direction of reaction at A?
See, uh, this is a reaction, correct? It's ra we got it,
Oh,
correct?
so it's just 20 degrees, yeah. So
Yeah,
you just
it's at an angle of 20 degree from horizontal. Okay.
okay, yeah, that's fine.
And how is that
Okay,
we
then
find the uh,
sorry, what were you saying?
yeah, one thing, see, you'll find rdx, correct? One thing, you'll find rdx doing moment balance, sorry, during doing force balance in x direction, and you do force balance in y direction, you'll get rdy, correct?
Yeah.
So suppose think that you got rdx in this direction and you got rdy in this direction, rdy and rdx, and how is that you, and what is that you'll have to do is you'll and let the resultant of these two be some rd, okay?
Yeah.
And rd, how is that you get rd will be rdx square plus rdy square, correct?
Yes.
And what is that angle? Let this angle be theta, and
It
you'll
was
get
tan theta.
tan theta is
Uh,
r dy by rdx. So that will be your
yep,
magnitude, and this will use this gives magnitude and this gives direction. Okay.
yeah, I'm good. Yeah.
Yeah. So
Can you move on to just skip the center of moment question for now and just move on to the
which one?
what was it?
That's
No, can you just move on to I think it's the last one. No, the very last, yeah, the last question.
the
Because
last one.
I don't really, yeah, the
The fifth,
last one,
the fifth one.
yeah, the fifth one. I don't really know how to do bending moments and stuff. So can you just explain to me the whole process and like any sort of notes you can add in the middle?
Yeah, we will do that. Okay?
Yeah, like not only this question, I just don't know how to apply the logic or like I don't know how to do this
Uh,
concept very well.
don't worry, don't. It's an easy one. So this is the P. So we have a hinge supported B.
Also, one second, I just had one tiny question, if
Yeah.
that's okay.
You can
Yeah,
ask.
so in different types of support types, there's like different forces that act on it, right?
Yes, yes, yes.
Like in this question. So is there I mean, I know you have to just remember all these like where sometimes like some forces like I think some forces have like an X and Y direction, some
Yeah.
forces only have a Y direction, some forces only have an X direction. So is there an intuitive way to know which force acts where in different types of pins, or do you just need to remember this information?
Yeah, so that I can explain with this problem only. You can see at
Okay,
B,
okay.
at B have hinged support, right? It's been hinged at B. This hinge support, this has been hinged at B. This will not let the beam move in this direction or in this direction, correct? It will not let the beam move in horizontal direction, neither in horizontal direction nor in vertical direction, correct? For that to happen, it should have two reaction supports, two reaction forces, right?
Wait, sorry. Does not let the B move up or to the right or left, yeah?
It will neither allow the beam move in vertical direction nor in horizontal direction, right? Because
Yeah.
it's been fixed, correct? So for that to happen, it should have two forces, correct? To resist the movement in two perpendicular directions, it should have forces in two perpendicular directions as well, correct?
Oh, okay. Okay, so X and Y in those cases.
Yeah. Whereas in C, it's free to rotate in it. It's free to move in this
The
horizontal
X
direction, correct?
direction. So the
Correct.
Y direction is the
Okay, it will only resist the force in y direction, nor in x direction,
yeah.
correct? So that was the case in the previous problem, right? You can see at A, no, this wall will not allow this ball to move in this direction, whereas it can allow the movement of this ball in this direction, correct?
Okay, okay, okay.
That's the reason why we took only reaction in perpendicular direction, not in this direction.
Okay, okay.
So which you should be careful with that, correct? So it's simple. If it resists the movement, we'll have to take the reaction. If it doesn't, you don't have to take the reaction force. That's it. Okay.
Okay.
That's it. If it resists the movement of the beam, you will take the reaction force. If it doesn't, you will not take. Okay.
Okay,
Got it?
got it. Yep.
Yeah.
Yep.
And we have a moment. We have a moment acting at A, that is 140 pound feet at the moment, and we have a distributed load till for about 1.5 feet. It is 28 pound per feet, and this length is big. This length is given as 3 feet, and this distributed load is for about 1.5 feet, and the rest of the distance is 4.5 feet. So that's the question, and we'll have to draw the shear force and bending moment diagrams for this. For that, before we draw shear force and bending moment diagram, the first thing that we have to do is find the reactions at both the supports. Okay? So that's the first thing that we have. And how is that we can find the support reactions? So the first thing in finding the support reactions, draw the free body diagram of the thing. That's it. So we have this. You can see at B, the moment is resisted in both the directions. So we'll have RBY and also RBX, right? Because it's being resisted in both the directions.
Yeah.
And at C, it'll only have RCY. Will not have RCX because it's free to move in horizontal direction. And we have a moment 140 feet and the distributed. So this is a free body diagram of this beam, and we can do moment force balance and moment balance to get the respective forces. And you can see if I do the force balance in x direction, let's do the force balance in x direction. I only have one force in x direction, correct, which is RBX.
Yep.
Correct. And that means and this whole beam is in equilibrium, correct? It's not moving in x direction, correct? Is it moving? No, right?
X.
It's
No, it's not.
it's at rest. The whole structure is at rest, and there is a force in x direction. See, there is a force in x direction, and the whole structure is at rest. That means RBX must be 0, right?
Yep.
Correct. With this, you can say the
Yeah.
force. So the summation of forces in x direction must be 0, and we only have one force in x direction, that should be 0. Okay. Right?
Yeah.
And let's do force balance. Summation of all the forces in y direction must also be 0. And we have two forces in y direction. The reaction forces, RBY and RCY, correct? Right?
RBY, yeah.
RBY
And
and
the
yeah,
the
and
the force on top.
yeah, and what is the total force of this loading?
Total 28 times 1.5.
Yeah, 28 times 1.5. That means we have two forces in upward direction, which is RBY and RCY, and the upward forces must be balanced by the downward forces. That is 28 times 1.5.
Yeah.
And this is one more equation. Okay. And we need one more equation, correct? Because we have two unknowns. We need at least two equations to solve for two unknowns.
Yep.
So how is that you get that? How is that you get the other unknown? You can see if I take the moment about point B. If
I have
see,
a question.
yeah.
So what exactly is that force that has like so many lines? Like how do you make sense of that?
So that's it's a distributed. That's we call it as distributed load.
Distributed load. Okay, yeah, I remember. Yeah.
Distributed load. So no, it's like this. Per feet, there is a load of 28 kilopounds. Okay.
Okay, so you just gotta multiply the whole thing by the
If
distance
if
that's applied to.
if there is a force of per feet 28 pounds, what is the force for 1.5 feet? You will just simply multiply with this distance. Okay.
Okay.
And you can see this is a distributed load, and there is one effective, we'll sum it up. Okay. So what is the total summation? 28 into 1.5 is the total load, correct?
Yeah.
And it will act, it will effectively act right at the midpoint of this. Okay. You can remove the, you can just remove the, after you after you find the resultant of this effective load, you can just remove the load which is present earlier, and you can represent with this effective load. Okay, got it?
Yep.
And that effective load is 28 times 1.5. It will act right at the midpoint of the total loading. Okay.
So that's 42.
It will be
Uh,
1.5 times 1.5 by 2 from this B. See this total is 1.5, right? 1.5 feet, right?
yeah. So 1.5 divided by 2.
Yeah, that would be 0.75. 0.75 feet from
Yeah.
B. Okay. So that would be the effective load of this. Okay.
And then
Of
the
this,
total force should be 42.
it is 28 times 1.5, 42.
Mm,
Then that's,
yeah,
yeah, yes,
I
yeah,
think
that's correct.
so, yeah.
Yeah. 28 into 1.5. Yeah, that would be 42. And that means you can remove the distributed load. You can just remove the distributed load, and you can put the effective load right at the midpoint of this distributed load, uniformly distributed load. Okay.
Okay.
So this we call basically, in generally we call it as uniformly distributed load. There will be also some other loads where there be uniformly varying loads. Okay. In this case, it's uniformly distributed throughout the length. Throughout the 1.5 feet length, it's uniformly distributed, which is 28 pound per feet. Okay.
What if it was uniformly, what if
Where
it was not uniformly distributed? Yeah, what if it was varying?
it's so
Like, where
it's
would the force be acting then? Every point
uh,
or?
yeah yeah. Let me suppose if in the same question, suppose at one end, suppose there is 28 pound per feet, and at the other, it's something like this. Can you see this is uniformly varying?
Yeah. I've seen these questions. Yeah.
And let at the other end it be 48 pound per feet. Okay.
Yeah.
And how is that you find this? How is that you find this? The total load will be the area under the curve. Okay.
Okay.
What would be the area? What would be the area of this? What would be this area? This is
I
basically a
mean, it's
trapezium,
just,
right?
yeah, it's just a trapezium. She's
Trapezium,
got a,
the half h into a plus b. Okay, where a plus
yeah,
b are the two parallel lengths and h is the distance between them. Suppose if that this is the distance between them, correct? Distance between the two forces. Let it be some 1.5, okay, 1.5 feet in this case. So that would be half into 1.5 into 28 plus 40. That would be the total effective load.
Okay, got it, got it.
And it will act. Okay, let me not go into it. Okay, if you have some questions, first of all, we'll solve this. Okay, we'll solve this question.
Okay,
And
yeah,
I'll.
yeah, we can do it afterwards. Okay.
Okay. And okay, so we were yeah, we did find out one of the equations simply by doing the force balance in y direction. And you can see we have two unknowns. We need at least two equations to solve for two unknowns. And how is that we get the other unknown? So we have so far done only force balance. Let us do moment balance so that we can generate the other equation. Okay. And you can see I can simply take the moment about point C, correct? But simply take the moment about point C, sorry, point C or point D. Okay, this is B and this is C. You can take moment about either of the points. By doing so, you can eliminate one of the unknowns, correct?
Okay.
Correct, because one of the forces passes through the point. That force can't create any moment, and and in your moment balance equation, you'll only have one unknown. Okay.
Yeah,
So
so then
you
you do it point B because then you remove RBX and RBY, so you just get more forces out of the way.
basically RBX is anyway zero, correct? So it's
Yeah,
like
yeah. So then you
both are
just
same.
fair enough. Yeah,
Yeah.
okay.
So let's do moment balance at B. And how is that we do moment balance at B? First of all, before you solve for moment balance, you write down all the clockwise moments and anti-clockwise moments, and you can equate them. Okay.
Okay.
Correct. We have one clockwise moment at B, correct? Created by this 140 lbf, correct? It is trying to rotate the beam in clockwise direction, correct? The moment has
Oh
been
yeah.
already given. Yeah. So one clockwise moment is 140 pound-feet. So let me write this clockwise moments, and anti-clockwise moments. So, and that's one clockwise moment. And this effective load, which is 42 pound-feet, sorry, which is 42 lbf, and it is also creating clockwise moment, right? At B.
Sorry, which one?
This one, this effective load. This effective load.
Yeah, it's creating a anti-clockwise moment.
No, it's clockwise. It's trying to rotate the beam like this.
Oh, the B bit. Okay, yeah, yeah, it is. It is
About
creating a
B.
clockwise.
We're
Yeah, yeah,
taking about B, okay? We're taking moment about B.
yeah.
So
Yep,
that
got it.
would be what? 42 times. What is the length? Length is 0.7 inch, right? 42 times 0.7 inch. Sorry, 0.7 feet. Sorry, 0.7 feet. So that would be the clockwise moment created by this effective load. And we have one more force, correct? This one, RCY.
Yeah,
And it
yeah.
creates and it should obviously create anti-clockwise movement so that
Anti-clockwise. Yeah.
yeah. So that would be RCY multiplied by what is the distance? So distance is 1.5 plus 4.5. That would be 6 feet. Okay, 6 feet. Okay, now we can equate these two. 140 plus.
Isn't it 1.5 plus 0.75?
No. We are taking moment of B, right? We should calculate all this length, total length. This
Oh,
one,
yeah, yeah. Okay, so okay.
this total length. It's already been given, right? 1.5 plus
Yeah, yeah,
4.5.
but then okay, but also like it wouldn't be 42 times 0.75, not 0.7.
Oh, sorry, it should be 0.75. Sorry, one and a
Yeah,
half,
that's what I was confused about. Okay, got it.
uh, half of 1.5, right? Sorry.
Yeah.
This would be 42 times 0.75. These are the clockwise movements, and that must be balanced by this anti-clockwise movement, which is created by RCY. RCY times 6. Okay. So you can see we have only one unknown here. RCY will be equal to 140 times 42 times 0.75 divided by 6. So this will be the RCY. Okay. And you can put this RCY here, you'll get RPY.
Sorry, can you go down again? I just want to
Sorry, this is,
140
yeah,
times
let's
40. Okay, yeah, okay, got it.
let's calculate this. Since we have to draw the free body, see, shear force diagrams, right? We'll have to let's calculate. So what is that you're getting? 28 point something?
One second. Yeah, I'm getting that.
28.583 lbf pound force. Correct?
Yeah, that's the one I'm getting.
Yeah. And we have one more equation, correct, from this force balance. So this is RBY plus RCY is equal to 42. Correct, from this force balance.
Yeah.
28 times 1. And from this we can find RBY. RBY will be simply 42 minus RCY. We got RCY 42 minus 28.583. 42 minus 28.583. So this will be 13.417. So that would be RBY. Okay. LBA. You got the both the forces? Like how you,
Yeah, I got it. I got it.
and we got both the forces now. So this would be the first step in drawing the, like finding the reactions at the supports will be your first step before you draw the shear force diagram. Okay. So when you're done with the reaction supports, support reactions, then you can start drawing shear force diagram. Okay.
Okay.
So let's draw shear force diagram. Shear force diagram. Before that, what
I
is
know this is like, yeah, I was gonna ask you what is shear? Like, how do you describe it?
yeah shear force? Let me describe shear force. Shear force is nothing but shear force. Generally, we define shear force at a section. Okay, what is a section? So this is a beam, right? So this is a beam. So I will take a section. Okay, something like this. A section, something like this. Okay, got it? So some
Yep.
and when I draw the section, when I draw a section at some point at some distance onto the beam gets divided into two parts, correct? So it will have a left part, left to the section, and right of the section, right?
Yeah.
And this whole thing becomes right of the section, and this small thing becomes left of the section, correct?
Wait, sorry,
You
can
understand?
you, why did you break that again? What would you do that for?
Yeah. So you see, suppose if I take a section here, okay, no, let me take a new
Oh,
section.
yeah.
So
You got it.
this
Yeah,
will be
okay.
the left of the section, and this will be the right of the section.
Okay.
For now, okay. For
Mm,
now, this is at this point. Let me call it a section XX. So to this section XX, this is left part. This is left of the section, and this is right of the section. Now,
okay.
having said this, shear force is nothing but shear force at a section, at this section, okay, at this section XX is defined by, it's nothing but algebraic summation of all the forces, okay, algebraic summation of all the forces, either to right or left of the section, either to right or left of the section. Okay, got it?
Yeah.
Now, what's this algebraic summation? Correct. So this algebraic summation simply means, we'll have to first of all, before you draw the shear force diagram, you will have to define the sign convention. Okay, that means if you are finding, we are finding shear force. What is this shear force? Shear force is nothing but algebraic summation of all the forces, either to right or left of the section. Before you solve for shear force, you'll have to decide, okay, using which side you are going to find the shear force. Okay. Suppose if I take, I'll find the shear force at a particular section using left part of the beam. Okay.
Okay.
Okay. So let me, and we'll have sign conventions accordingly. Suppose if I find a shear force at a section using left part of the beam, left part of the section. So and whenever you find the shear force using left part of the beam, all upward forces will be taken as positive. Okay. And downward forces will be taken as negative. Okay. And suppose if you find the shear force at the same section using right part of the beam, right part of the section, you'll take upward forces as negative, and downward forces as positive. Getting it?
Yeah.
These are the sign conventions that you must follow. Okay. So before you
Okay.
solve for shear force at intersection, these are the sign conventions that you will follow, and you'll have to mention, okay, in your exams also. Uh, these are the sign conventions you may follow. And now let's find the shear force. Okay, let's find the shear force. Let's stick a blank here, and you can see now. Let us take a section. Okay, let so what is shear force? Shear force is nothing but finding this algebraic summation at every pause at every section. Okay, that's the shear force
Okay.
diagram. Okay, that's the shear force diagram. Okay, finding the shear force
Yeah.
at every section gives you the shear force diagram. Now let's find a shear force at some. Let me take a section. So what is this point called? This is A, right? So this they are calling it as A. So let me take one random section between A and B. Okay,
Okay.
and I will find the shear force using left part of the beam. Okay.
Okay. So you took XX in this case, right?
Sorry.
You took
Yeah,
XX in this case.
yeah. That's any random section. That can be here. That can be here. That can be here. That can be anywhere. Okay, anywhere in between A and B.
Okay.
That's one random section, and you can also define this one as well. Okay, you can also define the distance as well. You can let me call it as
Is
X.
there a
Okay.
reason you take between A and B and not A from A to C, A through C?
First of all, no, you can see uh, in between B and C there is a load, right? Correct. There is this load coming.
Yeah, yeah, yeah.
So first of all, you will have to find a section where there is no, where there is constant load. You can see between A and B there
Mm.
is no load, right?
Yeah. Well, there
Then
is a constant load.
yeah, it's like this. Okay, so between A and B there is no load, and you will be deriving the general shear force expression between A and B first, and then B and C first. Now you'll be taking multiple regions. Okay,
Okay.
and you can see between A and B there is no load, right? That's the reason why I'm taking any random section between A and B. Okay,
Yeah, yeah. Got it.
and now let me take one random section which is at a distance x from A. Okay, and this random section is in between A and B, and I am finding the shear force at this section using the left part of the beam. And do I have any force to its left?
Yeah, you do. I
No,
mean, you
no,
have
we
a
don't have.
moment, not a
We
force.
have
Yeah.
moment. We have moment, not force. Correct.
Yeah, you don't have a force. Yeah.
So all that we do in finding the shear force is algebraic summation of forces, not moments. Okay. So
Okay, okay.
we don't have any force to its left. So the shear force, and that would be the case if I take any other section. Correct. If I take any
Hmm.
random section between A and B, it will not have any force to its left. Correct.
Yeah, you won't find anything. Yep.
Ah, that means shear force in this section AB is 0. Get it? Got it? Got it?
So,
We don't have any
so,
force. We don't have any force to its left
mm,
to do the algebraic summation, right? We don't have
yeah,
any
no,
force.
I got it, I
Zero.
got it. Yep.
Yeah.
Yep.
So that means shear force. Let me draw the axis.
Can you just draw it piece by piece, like that first piece, and then
Yeah, yeah. That's
so
what
on and so
I'm
forth?
doing.
Okay, yeah.
So we're just finding the shear force for a section in between A and B. Now we'll talk about B and C and all. Okay.
Yeah, yeah. Also, in A, if from A to that XX point, you got to include the bending moment as well, right? Because there's a moment acting on it.
Yeah, yeah. That will be doing in bending moment diagram. First, we are doing shear force diagram.
Oh, okay, just shear force diagram.
So just similar to shear force diagram, bending moment diagram gives the bending moment at any other section, at every section. Okay. Shear force gives
Okay,
shear force diagram gives
just
shear
the
force at every,
force.
yeah, just the algebraic summation of forces at a section, and and the bending moment
Hmm.
at a section gives the algebraic summation of all the moments to its left or right at a section. Okay.
Okay, got it.
Let's do this. I'm drawing this SFD, shear SFD. SFD, I mean shear force diagram.
And can you use the same laws that you did before, like the same sign convention?
Yeah,
If
we
it's
we, we
upward
are
moment, it's positive, downward moment,
yeah, yeah, that
positive.
that yeah, yeah.
Negative.
So
Okay.
first of all, let's draw the shear force diagram. So this is A, this is B, and we have C here. And you can see in between A and B, we don't have any force, correct? We don't have any force. So the shear force between A and B will be 0. Okay. Got it?
Okay.
Now
Yeah.
let's find let's find the shear force right at this section. Okay. An immediate section taken just to the right of B. Okay. An immediate section taken just to the right, immediate right of B. Okay.
Yeah.
And to the when I take an immediate section to the right of B, I have only the reaction at Y. Correct. To its left. Sorry. So this is let me not.
Are you taking the right of B or to the left of B?
So 1 second. So this is RBY, right? So this is
Yep.
RB. So at just at this point, this is point B. And if I take a section to the left, this is B. If I take a section to the left of B, and again the same thing follows, correct? There is nothing to its left, correct?
Yeah, there's nothing to the left. No, it's me towards the right.
That means I am taking a section to just to the immediate right of B. Okay, immediate right. Okay, and if I take a section just to the immediate right of B, again the same thing. This will be the left of the section, and this will be the right of the section. And I'll be finding the shear force using left part of the section. And you can see I have one force to the left of the section, which is RBY.
Oh yeah. Yeah.
So that means the shear force at a section towards immediate right of, to the immediate right of B. Okay.
Mm-hmm.
So let me. So this, and now what is RB? If I take a section, so I should have taken here. So if I take a section just to the immediate, sorry, just to the immediate right of B, just to the immediate right of, and you can also say there is also load on the top, right?
Oh yeah, there's a load on top as well.
But this distance, no, that the section distance I'm taking is almost equal to 0. Okay, that's immediate. I'm taking a section immediate right.
Mm-hmm.
So if that, and that means this distance D will be 0, almost equal to 0, right? Right.
Oh yeah, that distance dx. Yeah, you can just
Uh,
call it whatever.
yeah,
Tangent.
dx. So that dx will be almost 0. Then what would be this load? 28 into dx, correct? That load
Yeah,
in
yeah.
that part, that will be almost 0, correct? That's why I'm neglecting.
Pretty much. It's
Yeah,
negligent. Yeah.
yeah. So that means I'll have so if I take a section to its immediate right of B, I'll have only one load, which is RBY, acting in upward direction.
Mm-hmm.
So
Yep.
and what is RBY? What is RBY we got?
So the distance is negligent, so therefore only RBI acts.
Yeah, that's why only. That's when that is applicable only when I take a section to its immediate right. Okay, if I take a section at some other point, then that load also comes into account.
Okay.
Correct. So where
Yep.
is RBI? Where is RBI that we calculated? This is 13.41. Okay, we calculated it 13.41. So that means I'll have to draw here. So let me draw here. So to it immediate right. So since it's to its immediate right, I can just draw that on B only. Okay. So that means
Okay.
this is a load that is there. That is 13.417. Okay. Got it?
And there's a force going upwards?
Yeah, that's in upwards, correct? That's why I'm drawn in
Yeah.
up positive in
Okay.
positive y direction. Okay.
Okay, got it.
Now, now let's take a section and let's erase all this. Now let's take a section. Not to its immediate right, at some random location throughout this 1.5 feet. Okay, somewhere in between in this 1.5 length. So let me take one random section. Okay, let me take one random section which is at a distance of, so which is at a distance of x from A. Okay,
Yep.
now tell me, if I take this random section, now what, and this will be the left of the section and this will be the right of the section, correct? And we are
Mm-hmm.
finding the shear force using left part of the section. Now tell me, what are the loads to its left? We have RBY. Along with RBY, we also have one thing. What is that? We have one thing, the load, the distributed load.
Yeah, distributed about halfway.
Yeah.
So
Now
28 times 0.75.
20. No, it's not. That no. Now my section is not right at midway. It's some at random location. Okay.
Oh, okay.
Now
Got it. So
what? How
28
is that?
times
Uh,
something.
28 times. So this total distance is x, and um, this is AB. Now what would be this length? That would be 20. That would
Wait,
be x minus AB.
yep, x minus AB. Yeah.
So so the load created by that, uh, in this region, the uniformly load, that would be x minus AB, or AB is what, 28 times x minus, that's what is that, 3.
Imagine this is x. This is AB. So should be x minus AB, you say, right? So then it's 28. Yeah, okay, got it. AB, yeah.
And what is the sense of this? This should be negative, right? Correct. We are finding the shear force using left part of the beam. All the downward forces will be taken as negative.
Yes.
And we have RBY also as well, correct? Along with this distributed load, we also have RBY to its left.
Yeah, you do.
Yeah. So RBY. So RB, that would be PES, correct? The total shear force at this section will be, so let me call. So now, where is that we are solving? Yeah. Now we are taking a section. So 1 second.
So why did you take a section from A? Can you also take from C, or is it just you start from the left side because it's easier, or like
Sorry, I did not get.
uh why did you start from A and why not C or any other point? Or if you start from A, is it because A is the easiest to start from,
So the thing
and
is, we
then
have
you
start.
just
So we did also find the shear force in between A and B start from left side itself, correct?
Yeah.
So that's why I'm
Yeah.
taking. Okay?
Okay,
So
got
you
it.
can also take from C also, but the thing is, you'll have to stick with one direction. Okay?
Okay.
And now, what would be the general expression for a shear force? General expression for shear force for a section taken in between B, from B to 1.5 length. Okay, that will be plus RBY minus 28 times of x minus 3.
Yeah.
Correct. And what is RBI? RBI, what is RBI that we got? It's 13 something. It's 13 point something. Yeah, 13.4. So this will be 13.417 minus 28 times x minus 3. So this will be the expression. This will be the shear force expression for a section taken in between B and this till the uniformly distributed load ends. Okay.
Yeah.
And now you can see what
Wait,
is the ending point
this
of
is
this.
oh sorry, my bad. I just had a question. So this is the expression until the
Till no, this is the expression for a section taken between B and where the point. So this point till this point. That's it.
oh, okay. Okay.
Okay.
Yeah.
And correct. And after that, we don't have the distributed load, right?
Yeah. So as X increases until X. Yeah, okay, got
So
it, got it. Yeah.
let me also write the value for x. The value of x lies in between 3 and 4.5 feet. Correct. So
Yeah.
it's x starts at 3. Correct. This is the 3 where B starts, and this is 1.5. So this is 3
Yeah.
and this is 4.5, correct? So x will be, so this
Yeah.
expression is valid in this region only.
Okay.
Now,
Got it.
now tell me, what would be the shear force? What will be the shear force? What will be the shear force at 1.5? Just right at 1.5. So I'll have to I can substitute x in place of x. I can substitute 4.5, right?
Oh, yeah. Yeah.
So
At
that would
that
be,
point, you just take the left side. So then you just add up all the forces on the left side.
yeah. So that would be 13.417 minus 28 times 4.5 minus 3.
Yeah.
So this, what is that we get here? So that would be 13.417 minus 42, right? That I get it. That I'm
Yeah, you
getting
get
it as 20 minus 28.41 minus 28.58. Since I'm getting negative at C at this point, I'll have to draw in negative direction.
oh,
Correct. So this was what? What was this? This is plus 13.417, and a section taken to immediate rate of B. And right at the point where this distributed load
isn't
ends,
that to the immediate left of B? Oh, sorry, the immediate left of that
yeah,
point.
immediate right of that point. Okay.
Oh, immediate right of B or
Im
immediate right of that other point.
this one, no? This one, 13 point.
Oh, okay. Yeah, 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 yeah. Yeah.
That would be the immediate right of B. Okay. And
Yeah.
right at 4.5 length, I'm getting a shear force of minus 28.58. Okay. So since it's a negative,
Yeah, it's
I'll have
downward. Yeah.
the downward direction. And how is the variation in between them? How is the variation? It's a linear thing, right? Correct. It's linearly varying. Correct. We have x. It's a linear equation.
Yep. It's a linear
That means,
equation.
so that means you will have to just find the shear forces. This is minus 28.583, right? And just add them. Just point, getting it? I've drawn a straight
So
line.
wait, so you do negative 228.583 and then you draw a straight line connecting the two?
Yes, because it's the variation is a linear, right?
Oh, okay, yeah. Okay.
Had the variation been parabolic, I would have drawn like this.
Oh, okay, okay.
Okay,
Yeah,
connecting the
yeah.
same 2 points. Okay,
Mm-hmm.
and you got it so far. See, in between A and B, it's 0. Correct. In between A and B, it's 0. And right at to its immediate right, the shear force rises to 13.417. And at the
And
point
then
where the
drops to,
yeah, and it drops to minus 28.583, where the distributed load ends.
okay,
Suppose if I
I
want to
get it.
find a shear force at one random point, you can see. Suppose this total distance is 1.5, right? So
Yeah.
and suppose if at a distance of suppose at a distance of 0.3 feet from B, this will be the shear force.
Oh, okay.
At a
Wait,
distance of
so is there a way to draw this on a separate graph or do you just draw it on the diagram itself? Because my professor just draws it on a separate graph. After he writes down all the forces, he draws it on a graph and then he like tells us like,
uh,
oh, this is how it looks. Then he starts drawing it out.
maybe you'll have to define the coordinates like this. Suppose so we are taking the beam like this, correct? So we are taking the beam. So maybe you can also define the graphs. Okay? On y axis we'll have shear force. On x axis
Yeah,
we'll
yeah,
have
that's what he does. That's what he does.
on x. So on y axis we'll have shear force. This is A.
Yeah.
So this will be B, and this will be what? This is the point, some point where the shear distributed load ends. At B, I am getting a load of 13 point. Correct. This one. So 13.417 plus 13.417, and at the point where the distributed loading ends, I am getting a load of minus 28.583, and I'll have to connect linearly between them. Okay.
Okay. Yep.
So this will be the this will be the, where x is the distance from A, taken from A, okay? And that you can see, so this is 0. So in between A and B it's 0, and right to its immediate B, the shear force rises to 13.417 and it drops to minus 28.583, where the distributed load ends. So that's, and in between B and in between this, the shear force variation is a linear thing. Okay.
Yeah.
And again, sorry. So we have split the region into two parts actually. In between A and B, we had one shear force which is 0, and in between B and where the this distributed loads end, the shear force variation was linear. And now we'll take one random section between this where the distributed loading ends and C. Okay.
Okay.
So now let's take one random section between these 2 points. Okay. Any random section.
Yeah.
And you can see.
Yeah.
This will be the left of the section, and this will be the right of the section. Correct.
Left and right. Yeah. Got it.
And now tell me, which side would be better? Should I solve for the shear force at the section using left part of the beam or right part of the beam?
Right part. That's easier.
Correct. Because there is only one force to its right. To the left, it's complicated, but correct, because we have RBY, we also have the distributed loading.
Yeah.
So it would be easier if I stick for this particular region. If I stick to the right side, it would be easier, correct?
Yep.
And
Yeah.
to its right, I only have RCY.
Yeah.
And since I'm solving this using right part of the beam, so what is the sign convention I should follow? All the upward forces now will be negative.
And the right side, right? You said
Correct. Yeah.
right side, so it's upward, so it's negative.
Where is that? Yeah. So I've also
Yeah, so if
given
it's
the
upward, it's negative, right? Yeah, no, I
yeah,
I
it's
I wrote it down. I wrote it down.
yeah. And what is the let me take this section, and what the only force to its right is RCY. And what is RCY? That's what is RCY that we got? Where is RCY?
RCY,
Where is we get it as
RCY was
28.58.
28.5833.
28. That means, and that would be the same if I take any section, correct? If I take any random section, there will be only one force to its right. That means in this particular region, the shear force is same, correct?
Oh, okay, I see how it's equalized because when we found the bending moment in the previous, so the bending shear, the shear force in the previous is negative 28.583.
Yeah.
So when it reaches, okay, I got it.
So now this is C,
That's
and you
cool.
can see this from this point to this point, the shear force will be negative. That's it. That would be common, correct? At any section, it will so if I take any section in between this, the shear force is 28.53, 28.53, 28.53. It's constant. It's constant.
Oh, so from there you just draw a straight line.
Yeah, that's a straight line,
Like,
correct? Straight line is uniform, correct?
yeah, but
This
isn't a
is
straight line on the zero, not on
sorry.
like isn't it on this the x-axis like it's on the zero, right? Like it goes all the way up and just goes straight to the C.
No, it's not C. No, it's minus 20. You can see here, it is minus 28.5.
Yeah, and then oh wait, yeah, an upwards force of negative 28.
This
Okay,
is
okay, got it.
here. It's 0. It's minus 28.5.
Yeah, and then for the whole time there's an upward force. So from that point to the C ending, the whole time there's an upward force of 28.583.
Yes. Yes.
Okay.
So this will be the shear force diagram for your question.
Okay, got it.
So, and you'll have to define. Okay. So before you draw, you'll have to define the scale as well. Okay. You can take, so since you'll be drawing on a graph, you can take 1 unit on x-axis as 1 inch, 1 feet. Okay. 1 unit on x-axis. 1 unit on x-axis will be 1. So I think 1 second. So you know, right? So before you draw something, you have to give the units on the respective axis, correct? So the units, the scale actually, scale.
Sorry, what?
Yeah, no, so you will be drawing this on a graph, right? in your exam?
No, like they just tell us to draw like a rudimentary, like basic graph and like shows that you understand.
Okay.
Um,
So, that's no
yeah,
the thing I'm saying is the scale. Whenever you draw it on any graph, you'll have to represent the scale. So on scale on x-axis, so one, so you'll be having this blocks kind of thing, correct, on graphs like this.
yeah,
So this one, what is this 1 unit? So one on x-axis, 1 unit is 1 feet. Okay. So since we have, and on y-axis, 1 unit. So this one, this block, 1 unit will be one lbf. Okay, 1 pound force.
okay,
So this will have to represent before you draw something.
okay, got it.
So this will be the graph of this question, and this will be
And okay, so
vector.
this is just for shear moment. Now, if you do bending moment, do you still take the same points, or do you take
Yeah,
any
yeah.
random points?
So
And
so
then,
you can see. So from the question you should understand. Okay. So looking at the loading, you should understand. Suppose if I take no what like when you solve more and more questions, you'll understand what is the region that you have to take. Okay. No. So for suppose in this question, while we are solving for shear force diagram, in between A and B, I've taken any random section, correct, because to its left there was no force, correct,
yeah,
and the other section I have taken in B and C segment, and B and C segment I have divided into two parts, right? So one in bit where in this uniformly distributed region, that's one region, and after that the other region, correct?
yeah. So in this, it's
If
basically like you just take random sections and then
yeah,
you
it's
use like you just
uh,
feel like you just do the math wherever it makes the most sense, like whichever
yeah,
direction it makes the most, it's
yes,
easiest.
yes. So it's like this. Wherever there is force region, we'll have to divide that one region. Wherever there is no,
Yeah, yeah.
and so where no till where it's constant. Okay, you can see I've started
Okay,
I've started taking section at B, and I've stopped that where the loading ends. Correct. That's one region. I've divided it to one region. Okay, and
okay, yeah,
after where the uniformly distributed load ends till the end, because there was no load in between, then again, correct. Suppose if I add one more load like this, okay, if I add one more load like this, okay, then I would have split this one section and this region into another section. Okay,
yeah, yeah. You have
so that's
taken a point that's right before that when that moment that force starts, and
yes,
then find the shear force there, and then you take a then from that point you'll take another point that's right after the force ends,
yes,
uh, and then you find the shear force within that entire block.
yes, exactly.
Okay, got it. Yeah.
So now let's draw the bending moment diagram, BMD, for the same, and you can see. Now tell me, what are all the regions I should take? Should I take
So in bending moment, I just want to confirm, you use the same exact points you took before, right? Or you can change it up.
we can use exact points. Okay.
Okay.
So, and before I draw BMD, let's define the sign conventions. Okay. Just like how we defined the sign conventions while drawing the shape diagram. For BMD, if I solve again, correct, we'll have left and right sections.
Yep.
Suppose if I solve for BMD at a section using left part of the beam, all uh, this all counterclockwise, all clockwise movements will be taken as negative. Sorry, take clockwise moments will be taken as positive. Okay, and anti-clockwise moments will be taken as negative. Okay, and similarly the other thing, if I solve for the BMD using right part of the beam, anti-clockwise moments will be taken as negative positive, and clockwise moments will be taken as negative. So these are the sign conventions we follow. So while we draw BMD diagram, bending moment diagram. Okay.
Yep.
Yes. And so now let's get back to our loading. So you can see now let's take a random section between A and B. You can see if I take one random section in between B and D, the beam gets divided into two parts, left and right. Now, suppose if I solve for BMD using left part of the beam, do I have any moment for a left part of the beam?
Left part you do, yeah.
Yes. What is that? It's
The
140.
140 LP,
Yeah,
yep.
140, and that's in clockwise sense
It's yeah, it's a clockwise, so it's positive.
about this section. That's in clockwise sense about this section, right?
Yeah.
So that would be positive. Okay. And that would be the case. That would be the case if I take any random section in pin A and B. Correct. I have only one moment to its right.
Yeah, regardless of what you do there, yeah.
Yeah. So that means. So let me draw BMT. So again the thing. So this is BMD, bending moment on x-axis, and distance on bending moment on y-axis and distance on x-axis. And this will be point A, where the thing starts. And right at point A, what is the bending moment? Correct.
140. So there's a constant line of 140 in the
Till
positive
B, right?
direction
Till
till
B,
B. Yep.
correct? In positive till B.
Okay.
So this is how. And what is this? This is plus 140.
So if the shear force is changing linearly in the first diagram, in the bending moment, would it change parabolically?
Yes, yes, correct, 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 correct.
I'm just guessing. I don't really know. So yeah,
Yeah,
can you explain why?
I'll explain. Okay. So there is a variation. No, there is a relation between shear force and bending moment. Okay. If the bending moment, if the shear force varies linearly, what is linearly? Order one, right? X power one. That's what we say
Yeah,
linearly
yeah,
vary.
yeah.
If shear force varies, if the order of shear force is one, then the order of bending moment in that region will be two. Okay. Suppose if shear force varies parabolically, then bending moment will increase by one more order. It will vary cubically. Okay.
Oh, okay.
The order increases by 1 unit. Okay. If the shear force is
Okay.
constant, suppose if the shear force is constant, okay, that means what is shear force is being constant, order is zero, right?
Or a zero. So
Then the
um
bend then the bending moment will rise by 1 unit. Okay.
so wouldn't this be linear then? So wouldn't this be like x to the power of one? So wouldn't it be a oh yeah, it is. Never mind.
Sorry.
No, I got it. Yeah, sorry, go ahead.
And now this between A and B, right? Sorry.
Yeah.
If the
Well,
bending
right
moment, sorry,
before B.
1 second. If the bending moment, sorry, if the shear force in a particular region is zero, suppose, okay, if the shear force in a particular moment is zero, then the bending moment in that particular moment will be constant. Okay.
Okay.
And if the shear force is linearly varying, bending moment will vary parabolically. If the shear force is varying parabolically, bending moment will vary cubically, and the things go on. Okay.
Okay.
Uh,
Constant.
okay.
And
Now,
sorry, let me if you said if shear force is
so sorry,
uh
if
linear,
shear force in if shear force is varying linearly, if shear
yep.
force varies linearly, if the shear force has got a order one, then bending moment will have order two. And if shear force varies will have if it has got order two, then bending moment will have third order. Okay? And similarly, if shear force, if it is varying cubically, then bending moment will have a order four. And if shear force is zero, shear force is zero, then bending moment will be constant.
Okay.
Got it?
Yeah.
You
So it
can
just
see in
increases by
between
one power.
in between A and B shear force was 0, correct?
Yeah.
But bending moment is constant,
Yeah,
right?
yeah, yeah. But that is because there was a moment there. If there was no moment there, then even the moment would be zero.
Uh, that even 0 is a constant, right?
Ah, yeah, that's also fair. Yeah.
Correct. And now let's take a section between B and till where the loading ends. Okay.
Yeah.
And now tell me how is that we calculate the bending moment? How is that we calculate the bending moment? So
So
suppose
in this point, we took a moment from A to a point right next to B, not at B though. Like
uh,
a very
uh
negligent distance to B.
yeah, that you can consider. Okay. Yes, correct.
Okay.
Now
So
if I
now we'll take a point after
now
B.
now let's take a section after B at some considerable distance. Okay.
Okay.
And suppose that distance from A bx. Okay. Okay, the distance of that section from A B some x. Okay. Now
Yeah.
what are all the moments that are creating what are all the forces which can create moment about this section x?
The upwards and the
What?
downwards.
Yeah, so the rby can create some moment, correct, at this xx.
Yeah.
What is the
Yeah.
moment created by rby at this xx? That would be
That would be
rby times x minus 3.
anti-clockwise.
That's anti-clockwise. Okay. uh, that's anti-clockwise, but what is the moment created? That would be rby, and the distance is x minus 3.
Wait. X is
This
the
part,
entire thing, 3 is that, so just that tiny bit is x minus 3, right? Yeah, yeah,
yeah,
it would be RBI times x minus 3.
yes, that would be. Now I'm finding bending moment at this x. Now the bending moment at this x would be what? uh, so there are two forces that are creating bending moment. That would be rby rby times x minus 3.
Wait, why x minus 3 though?
This is the distance, correct? So this is the distance, correct? That distance is x, the total distance is x, and I'll have to subtract this 3.
Yeah, yeah, yeah.
So,
Okay, okay, got it. But you could
correct.
also take RBI and one times it by 3 to find the moment in the other direction from A to B.
Sorry, I did not get you, please come.
If you have so RBI, the force RBI,
Yes,
RBY, sorry.
yes.
You multiply that force RBI times the distance, right? The perpendicular distance. Couldn't that also be AB? Like 3, just 3?
No, we are taking moment about section x, not about a.
Oh, okay. Sorry. Yeah, go ahead. Yeah.
But we are finding bending so all the algebraic summation of all the bending moments at this section x. Okay.
Okay. Yeah, sorry,
So
go
that,
ahead.
and again that would be positive. What is the sense? Positive, correct? Since we are taking from the left part, left plot
Yeah.
from the left part, anti-clockwise moments will be positive. Okay.
Oh, x minus 3. Okay. I got you.
So
I got
that
you.
that would be plus. Okay. That will be plus. Now, what are the
That'd
other
be,
moments that we have to its left?
yeah.
What are all the other moments that we have to its left? We also have one more thing, plus 140.
Yeah, we do have plus 140.
Plus 140. That's one more thing. And we have one more moment created by the load above it. Correct.
A
The
clockwise
the
moment.
distrib
Sorry,
the
I'm
dist
just making sense of this.
so
So
the, we
RBY is, yeah, okay, yeah. Sorry. Yeah, go ahead. It's plus 140.
plus 140. We have added two more. Now we'll have to algebraically add one more thing. The moment created by the distributed load from B till this section X.
Yeah, by the
Yeah.
upward
Now,
force.
now, now tell me what is a effective load in this region?
That's 28 times x minus 3.
X minus 3. And where is it effectively acting?
In the middle of x minus
X,
3, so half of x minus 3.
that would be half of x minus 3, correct?
Yeah.
So now that would be, and that is negative, right? It's in clockwise sense.
Yeah,
So that,
negative.
now tell me, what is the force? Force is 28 times x minus 3, 28 times x minus 3, and that is effectively at a distance of x minus 3 from the sections, correct?
Oh, okay. I got you.
You can
Yeah.
see,
So it's parabolic, so there's an x
no,
squared
you
there.
can see x minus 3, x minus 6, there is x minus 3 whole square.
Yeah.
Now this is how you get the parabolic variation, okay?
Ooh.
So that's a reaction. And now you can simply substitute 4 in place of x, you can simply substitute 4.5, so that you will get the bending moment at the point where this loading ends, okay? Correct.
Yeah.
So shall we do that? So in place of RBY was 13.417, RBY was 13.47 into 4.5 minus 3 would be what? 1.5, 1.5 plus 140 is there, plus, sorry, minus 14 into 1.5 into 1.5. So I'm getting it as 128.625, okay? That means, so where is that? Yeah.
Wait,
At,
you
uh,
just
so in
oh, you
place
took
of x, I
excess
sub,
4.5?
yeah, x as 4.5, correct? X as
Okay.
4.5. And also one more thing that I'll have to tell you. This bending moment variation is valid only in this particular region, okay?
Which particular region?
Where the x starts from 3 and ends at 4.5.
Well, yeah, okay, got it.
Okay, this x, so x is valid only in this region, okay?
Okay, understood.
After x is greater than 4.5, there is no uniformly distributed load, right?
Yeah, there is no.
Okay, and when x is less than 3 also, there is no distributed load, so it's in between 3 to 4.5 only.
Okay, yeah, I got it.
So, and now right at 4.5, I got it as, I simply substituted x is 4.5, I got a 120, the moment I got as 128.65, okay? 128.65, and that's negative, and that's positive as well, okay? I'm getting a positive moment.
Yeah.
And I got it this. So this is 140. So this is one. So this should be less than 140. And how is that I should draw these 2 points? I should parabolically add.
Wait, what was the answer you got, by the way, for
So
bending moment?
I'm getting plus 128.
Plus 128. Yeah, I think I got the same thing.
So one second. So this is what I should add. Got it? The parabolic variation.
Yeah.
And so, and
Wait, why
now
is it a downwards parabola? Why isn't it an upwards one? Because in this case, it's positive x squared. Oh, no, it's negative. Yeah, you're right. Never mind. You're right.
it's a negative thing, right? The the
Yeah, no,
the
I
the
saw it.
sign of the sign of x square is negative.
Yeah, I
Sorry,
just saw it.
the coefficient to the x square.
Coefficient of, yeah.
And also, yeah, now let's take a section in from C to, sorry, where this loading ends till C, okay?
We'll see, yeah.
And now tell me,
The right
which,
side.
yes, yeah, you are getting it, correct. If I take the moment, if I calculate the moment using the right side, because there is right side, to its right, there is only one force, and that one force can only create the moment, and that moment should be
Yeah.
what is the sense of that moment? If you are, since we
It's
are
on the
calculating
right
from the
side.
right side, anti-clockwise moments will be positive.
Positive, yeah.
Now that would be what? That would be now.
RCY times.
Now let's Uh,
4.5.
yeah. And also, what would be the moment? What would be the moment right at C?
What would be the moment right at C?
Right at C. What is the effective? What is the summation of all the algebraic moments right at C? It should be zero, correct?
0, yeah.
Because there is no distance, correct? Since
Yeah,
there is no distance, and that means you can see where is the bounding moment diagram that we have. So and at C, at C it's zero again. It should be on x-axis only.
yeah.
And now now tell me one thing. In and what is the shear force variation between B and C? Sorry, in this region,
Uh, in that region, it's shear force is constant.
shear force
So
is
the
when
shear
shear force,
force is,
then the bending moment variation should be linear, right?
yeah.
That means I can simply join these two. Got it?
Wait, shear force is constant. I don't think you wrote that down. What if shear force is constant, then bending moment is linear?
Sorry. One more thing I have not written here. So let me. Okay. I got it. Okay, 1 second. So this is a thing, right? And one more thing I'll add to it. So if shear force is a constant, okay, apart from zero, okay, being zero is also a constant. If shear force is constant, then bending moment will be linear, okay?
Hmm. Okay.
Okay.
Yeah. Got it.
You understand now? So in between this two
Yeah,
points,
I
shear
get it.
force was constant. So I can simply join these 2 points. So this
Yes,
will be the
yes, understood.
so so this will be the shear force variation. Sorry, bending moment variation throughout the length.
Okay. Yeah, I
If
got it.
you can they can just give you the length, like they can say what is the bending moment at a distance of 4 point from at a distance of, suppose, let me say 4 feet. So 4 feet falls in this region. So you can say this, you can on this graph you can simply say this is the bending moment at that point.
Okay. Yeah, got it.
So that's how this varies, okay?
Yeah,
So
I
the
have
thing is,
the next question I have is, I mean, okay, sorry, go ahead. What were you saying?
yes, what's the next question that you have?
Yeah, no. You can just go ahead. What were you saying? Because I was gonna give you a question from a different thing. I was just gonna send you another PDF.
Yeah, you can send it to me, we'll solve that.
Yeah, I'll just do that 1 second.
uh, 1 second, are you there?
Yeah, I'm still here.
I'll join again. I don't know. It's there is a lag when I write it. I'll rejoin again. Okay.
Okay, all right. Should I leave this meeting? Just leave it. Or I should probably.
Hello. Yes. Hello.
Yeah,
Yeah.
yeah,
Shall we?
hello.
Have you sent me this question?
Yeah, I sent it to you. I sent it to you.
One second. So yes. Let me check it. Yes. Which one should I solve?
The question, I think it was, what did I send it to you? The question 5. I don't, I don't understand how to break the values into r, theta, and then so on and so forth.
Okay. So is a car is that one, right?
Sorry, which one is it? Yeah, the car is moving. Yep, that's the one.
It
Like, how
says
would you? I don't get that concept. So can you just tell me like all the rules and like whatever, like any information I need to know more than this question related
okay.
to
Okay.
the topic? Yeah.
A car is moving to the right along the road as shown away. When it reaches a point depicted, its velocity and acceleration are as indicated. Okay. Considering the polar coordinate system indicated. Okay. Find at this instant the values of r, theta, r dot, and yes, and also theta dot
So is
r.
r dot just velocity and r double dot just acceleration?
R dot is r dot is velocity, but in that radial direction. Okay.
Okay, yeah. What is that? How does that mean? What like how would you do that? Or like
Yeah.
why
Yeah.
would you use a radial?
So
Or how
just
would you use it?
okay.
So like,
So this there is a horizontal thing, and you started at this point. So O. So O being the center of the system, and we also so when the car is at this particular location, which is at a distant radial location r, and theta is the angle from the vertical distance. So this is B. This is given as B. So this is B, and this is R. This is B, and this is V, and this is A. So A and V are the accelerations in x direction. Okay, in A and V are accelerations in x directions, and at this location B, D, V, at this point they have given all the values, and we have to calculate the R. So how is that we can calculate R? So B at this particular location is given as what? B at
or
this
you can just
particular,
use like Pythagoras theorem, right?
yeah, this is 500 feet and this is 450 feet. So
In an
R is
actual
a rate.
question, would they give us R? Like, would they give it like this, or like do you have to just use a different? Like, what is the point of using an R? Or like, how do you even use this, or why use this? Like, I don't get it.
So actually, no, they just want,
Is this like a
suppose,
different way to express it?
no. So the thing is, no, whenever there is circular motion, we know about some center, we know there is radius about which it rotates, correct? And all,
Yeah.
and the after some time it might have covered an angle theta and all that. So basically, this is circular coordinates, or you can say. So in this question, it's a different one. No, it's not a general thing where used in every question. So in this question, they just want to define some r. That's it. Okay, they
Okay,
just
got
wanted
it.
to define some r. Okay? This is valid to this particular question, and this is not in general. You will be using for any other concept. Okay,
Okay.
and you can see you can just calculate r using Pythagoras theorem, right? So,
Yep.
so that would be what r is b square plus d square. Okay, and now
Yeah, and you can do the same thing with theta with the angle, right? Tan
and
theta.
now uh, the angle. What is angle?
Like if
One.
you want to find theta.
Yeah. Let me first of all let me solve this. Okay, so the r
Yeah, yeah, sorry.
r is what? R will be under root of b square plus d square, correct? So now
Uh-huh.
uh, b will be constant. Suppose let the uh, one second, let me extend this. Suppose after some time the car will move to a new position, correct? Correct. Now,
Hmm.
correct,
Yeah.
correct. And in this particular and this will be your D. Earlier
Yeah.
D was still here, just this, and that means because the car is moving in this direction, B won't change, right? B will B change? B won't change. Correct. In any at
No.
any location, Pythagoras you can use Pythagoras theorem, and in this Pythagoras theorem, the one thing that doesn't change is B. Correct. Only D changes.
Yeah. No
Correct.
D changes. Yeah.
And you can see. Let me differentiate this R with respect to time. Okay. So let us do dr by dt. Okay. Now, what is the differentiation of this? What is the differentiation of x? So this looks something like this. Correct? B square plus d square 1 by 2, right?
Or by dt. Yeah. Yeah.
Yeah. So if I do dr by dt, and I'll have to differentiate this with respect to dt, and you can see what is the differentiation? It will be half b square plus d square 1 and half minus 1, and I'll have to differentiate the thing inside. Are you getting it? So this is
Yeah.
how
You have to
differentiation
differentiate the
works.
entire thing inside. Yep.
Yeah. So the entire and b square will b square changes with respect to t, will b change with respect to t? No, right? Yeah, whatever time
No,
you
it
take
won't.
b, that means b square is a constant with respect to t,
Yeah.
and that
Only
means
D
that
changes, right?
yeah only d changes. And what is the differentiation of d square? That would be 2 uh,
2D.
uh, d of d by t. Okay, let's not take this as d. Okay, it's a bit confusing. So let me take it as some k. That let us take the distance as k. Okay, or s. Okay. So when I do differentiation, that's that d and this d are matching. Okay, that's what I change. So it will be r b square plus s square, and this will be b square plus s square, and s changes with respect to time. Correct.
Yeah.
And that would be what? And the differentiation of s. What is the differentiation of s square? 2s ds by dt.
Yeah.
Correct. You got it. You got this differentiation.
Yeah, the
And what is dr by dt? Rate of change of r.
velocity.
So wait, rate of change of r, that is r dot,
Oh, okay.
and that would be half of. And what would be this? 1 by under root b square plus s square. Correct.
Oh, okay, okay. B
And this will
square
be
plus.
2s. And what is ds by dt? Rate of change of length. That would be velocity of object in x direction.
Yeah, got it.
So now this will be r dot.
Oh, is that it?
Yeah, that's it, r dot. And what is r dot at this particular location? At this particular location, you can see the s is given as what? The s is given as 450 feet. Correct. At that particular location. Correct. Correct. At this particular location, s is given as 450,
Yeah.
and let's put 450 in case of s, and b is anyway constant, which is what? Which is 300 feet. So 300 square plus 450 square. And what is the velocity in this particular direction? At this particular location, you can see the velocity is given as 120 feet.
Yeah.
120 feet. So in place of velocity, I'll put 120 feet per second. 120, 1 second. So that will be 120 feet per second. That will be r dot at this particular location. Okay. At this particular instant. Sorry. At this particular instant, I'm saying. Got it?
Mm, okay, okay, yeah. So what is so theta when it's like when you differentiate theta, what is the value for that? What does that mean? Like what do you mean by differentiating an angle?
We
What do
have
you get by doing that?
we haven't included theta, right? So far. So let's include theta now. Okay.
Okay.
And how is that we can include theta? Let's find tan theta. Correct.
Okay.
Or what tan theta would be s by b.
The way my professor does it, he like draws like directionally, like he draws like some lines, like he like he draws the actual thing and then he draws the direction of V and then V theta and then R theta and then theta. Like he does something like that. I don't really know how he does that.
Okay, that's what he has used. Okay.
Yeah, yeah. I think he wrote, yeah, he's like draw the R and the theta axis at the car's locations, use geometry and trig to find R and theta at this location. So
Uh,
he doesn't really use differentiation. He just uses geometry and trigonometry to find R and theta. Then project like he's written all of the things on that document. I just don't know how he does it.
okay, okay. That you can, yeah, that's one way of solving. Yes, correct. You can also do this way. The thing that he has done is, uh,
Like this, your way makes more mathematical sense to me. His way is more what he does. So that's why I was just trying to understand what he does.
the thing what he has done is right. Uh, See, let me explain. You can see this is the x direction velocity of this object is v, correct?
Yeah.
And we can split this velocity into two parts, one perpendicular to it and one along the radial direction.
Oh, okay.
Okay, and
Yeah.
this will also be theta.
Yeah.
And what is v cos theta here? This will be v cos theta, and this will be v sin theta.
V cos theta is just equal to R.
Yeah, r dot is just equal to v cos theta. Correct. That, see,
Sorry, yeah, R.
whatever the velocity in that particular direction, that's the radial change with respect to time, right? At this given instant.
Okay, so if you just do a b squared plus d squared and then under root that and
Yeah.
equal it to R and then differentiate, but if you differentiate that number, it's a zero. So, oh, and then you find V cos okay, okay, I kind of understand what he's
And
trying to
what
do
is
with that.
V is 450. Correct. At this particular question, V is 4. Oh, sorry, oh, V is not 450. What is V? What is V? 120, right? 120. Sorry.
Yeah,
V is 120. And what is cos theta? Cos theta, you can find this triangle with the help of this triangle, correct?
yeah, you can.
What is the cos theta that you can find? That would be a B by R,
Yeah, you can find
and
B by R, yeah.
R is under root B square plus D square, correct? So that will be cos theta would be from this triangle would be B by under root B square plus D square. B by under root B square plus D square.
Yeah, you
So
get
that
66.57 total.
and one second, what is that you are getting?
66.57.
That's the answer, correct?
Yeah,
You can also see mine gives the same. You can see 2 gets cancelled. We are left with b into d by under root b square d square, and that's what we have here. B into d by under root b square plus d square. Okay,
oh, so you get the same answer.
yeah,
Yeah, yeah.
you'll get the same answer.
Okay, we can use your method. Your method makes more sense to me.
And yeah, what are the other things that we need to find? So we have we
R double
so
dot and
yeah.
theta now dot and then so on.
So far we have found out r and r dot, correct?
Yeah,
And you can see. Let me also uh, see. Uh, what is r dot from my method? So r dot from my method would be, so we'll solve both the ways. Okay, we'll be solving this question. Once r dot, what is r dot that have? It's 2s into v by under root b square plus d square, right? Sorry, b square plus
yeah.
s square.
I mean, it's just
B,
S into V, right? Because the twos get canceled
yeah.
out.
Sorry, yeah, yeah. That 2 gets cancelled out. So it's just s into v, s into v by under root b square plus d square. And you can see s, what is s? S is the distance, correct? S is the distance from that x, and it's a function of time, and b is also a function of time, and s is also a function of time. So double differentiating this becomes a huge thing. Okay, so double,
Hmm.
you will get a big expression. So let's not go this way. Let's use the way your professor has solved. So from using your professor's way, r dot is simply v cos theta. Correct.
So what he basically did was,
Correct.
he just did
you're
V
getting it.
this way,
So the thing is, this is v,
then
and you have split the v into two components, one along the radius and one perpendicular to the radius. Okay.
yeah, okay,
And along the radius becomes a radial component, that is r dot, which is v cos theta. Okay.
yeah,
Got it? Yeah.
yeah,
And you can
understood.
see this is r dot. This is r dot. Let's double differentiate this. Okay. This is r dot. This basically r. What is r dot? dr by dt, which is v cos
Yeah.
theta. And you can see even theta is a function of time, right? Correct. With time, theta
Oh
changes,
yeah,
right? It won't be constant.
yeah.
And even v is also a function of time. Correct. The velocity will also change with respect to time. Correct. So
Yeah.
that means we have two components here, two values which are function of time. So r dot what does let us double differentiate this. That becomes r double dot. That would be v cos theta d. Sorry, keeping v as constant. If I differentiate cos theta, that would be minus sin theta, and theta is a function of time, d theta by dt. Correct. And again, putting cos theta as constant, I'll have to differentiate v, which is dv by dt. So this is how the multiplicity rule works, right?
Oh, yeah, got it.
Correct. And what is d theta by dt? This is what is theta dot.
Oh, okay.
And what is dv by dt? It's acceleration, rate of change.
Acceleration.
So now r double dot will be equal to minus v sin theta dot plus cos theta into a. Okay. This
Yeah.
is this will be the expression for v dot or double dot. Sorry. And the thing is, we don't know what theta dot is, right? We know theta, we know v, we know a. So far theta dot is not found out. Let's find out theta dot. Let's find out theta dot. You can see from that expression, from the triangle, what is tan theta? Tan theta is s, right? D by b. Sorry, d by b.
Yeah.
Correct.
Yeah.
And what is let's differentiate with respect to time. So if I differentiate this with respect to time, what is the differentiation of tan theta? Secant square theta, right?
Yeah.
Yeah. Secant square theta d theta by dt, that will be equal to b is a constant, b db by dt. Correct.
Wait, B is a constant or dB? No, isn't it dt by dt? Because because d changes, right? Or what is it? Sorry.
Yeah. Sorry. It's d of d by t. Okay.
Yeah, so d of s by whatever that you changed
Uh,
it to.
yeah. Let me call it as x. Okay. Let me call it as s. If I call it as s, ds by dt. Okay. Now this becomes theta.
Okay.
This is theta dot. Theta dot will be what? And what is ds by dt? Velocity, rate of change of displacement in acceleration. So it will velocity by b, and this secant square theta
Yeah.
comes this. Secant square theta comes this side, and we can theta as cos square theta. Okay. So this will be theta dot.
Well, if
Uh,
you do my professor's method, what would you do for theta dot?
so
Theta
let
dot.
theta dot. So theta dot. Now let's. So this is what this is all related to mathematics. Okay. So the mathematical way of solving it. What would be theta dot? I can say, and you can see. Let's go back to your professor's way. Okay. So what is r dot? R dot what v cos theta. Correct. That you understood. The radial direction.
Yeah.
The
Yeah.
radial component of velocity would be written. And what is the perpendicular component of velocity? V sin theta, right? Perpendicular to the
Mm-hmm.
radius. And now,
Yeah.
uh, so for something in circular motion, what is the formula? V equal to R omega. You must have heard, must have known this, correct?
Oh yeah.
V, that would V equal to R omega, right? V equal
Mm.
to R omega. Now, what is V here? V here is V sin theta,
Yeah.
correct? Let me,
This
so
is for
for your,
centripetal.
yeah, yeah, let me draw one circular, big circle, you'll understand. No, this, with this being the center, okay?
Oh, that's tangential.
Okay, V sin theta becomes tangential and V equal to R omega.
So E cos theta is equal to R.
No, V sin theta. V sin theta is tangential, okay? No, you know this, correct? Suppose if something is circular motion, if
Yeah. No.
let the radius be R and let the tangential velocity be V and
Mm-hmm.
let the angular velocity be omega. Now we can relate V equal to R omega.
Yeah.
And now what is the tangential velocity here? V sin theta.
Mm-hmm.
Now that means V sin theta must be equal to R omega,
Yeah, it
correct?
does.
And what is omega? Rate of change of angle,
Oh,
which is theta
okay.
dot, which is theta dot,
Theta dot.
correct? And from this theta
Got it.
dot would be what? V sin theta by R.
R, yeah. V by
That's your
R.
professor. That's your professor's way of solving. Okay? And that's a simpler way as well.
Got it.
And you have every value now. You have R, you have V, you have theta. You can find sin theta, and you can find theta dot. Okay,
What about double dots?
and you can just differentiate it. Okay, just differentiate it.
Oh,
You'll
just
get
differentiate one more time. Yeah. Okay.
differentiate it one more time. You'll get double dot.
Okay.
That's it.
Um,
So
yeah, I think
that's
that's
I think we have found everything. Correct. Theta dot, R double dot.
yeah.
Yeah, that's it.
Mm-hmm. Yep. Also, like in friction, like if I'm doing friction questions, right?
Where
Um,
are
like, do
there
you want an
any?
example? Should I send you an example or?
You have sent me an example. Yes.
Um, yeah, I'll just have to send you an example. Yeah.
There is one question here actually.
Is there? Yeah, I think the first question is friction, pretty sure.
Yeah. So what is that to be found out here?
No, I think I kind of understood this, but in the sense that in these cases, right? Um, I think in this case only static friction is given. Yeah, in this case only static friction is given. So how would you find the largest P and the smallest P? Like in the sense that like would the largest P be the value where it's the smallest friction?
Mm, the smallest peak consists.
Because
Uh,
in this case, if it's largest or smallest, you need to like vary it depending on where which side the friction is handled. Because they don't tell you which side the friction is or which side the block is sliding. So the P could be any
oh
value.
yeah. So suppose if it is moving above up the plane, you will get one p. If it is moving down the plane, you will get one p. Getting it?
Okay. And that
Uh,
varies because of the frictional forces.
yeah. So suppose if the block is tending to move downwards, okay, and if the block is tending to move downwards, the friction will be up the plane, correct?
Yeah.
And that means if the friction is up the plane, then you can see you'll have to you'll have to push only a little amount because friction is helping, correct? Are you getting it? You only have to apply a little load because see
Yeah. Okay, no,
because
I understand.
block is moving. So suppose you'll have to first decide block is tending to move down the plane. If the block is tending to move down the plane, the friction will be up the plane. So friction is also helping to resist the block's movement. So you only have to apply little force. Okay. Now one you consider block moving down sorry, we consider up the plane, right? So we consider down the plane. Now let's consider block is moving up the plane, tending to move up the plane. Okay, the block is tending to move
Yeah.
up the plane, then friction will be in opposite direction. Correct. Now, in order, now your friction is in upward direction, you'll have to apply more force in the second case. Okay, that will be the smallest and the largest p. Okay, are you getting it? So should I solve it?
Yeah, no, yeah, no, no, I got it, I got it. Yeah.
Correct. No, in which case, if it is
Yeah,
tending to
yeah.
move down the plane, you will have one P. If it is tending to move in up the plane, you will have one more P. It depends on the frictional direction. That's it.
Okay, yeah, okay, I understood. Also,
You and in both the cases, you will be getting two different P's, and which one will be larger and which one will be smaller, you will decide.
okay, 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 understood, understood. And also, I had like one more tiny question if you have the time.
Yeah, yeah. Please.
Yeah, I just need to send you like an example. I just need to ask you if the forces are balanced properly. That's about it.
Okay.
Like, there are some questions where I've done where you need to like use Newton's second law, right? So in those questions where the block is moving like downwards or a block is moving upwards or whatever.
Yeah,
So
yeah,
in
yeah,
one direction, yeah, in one direction, like the force need to be balanced. So one direction needs to have all the force, other side needs to be m times a because all the
yeah,
force in one direction needs to be balanced, right?
yeah. So you'll have all the forces, in a particular direction that will be equal to m times a.
Yeah, okay. So in those kind of questions, sometimes you include m times a, sometimes you don't, or I don't get it. Like sometimes I see some answers where
Yeah, suppose
they,
no, when is that you don't include m times a is no, when the block is just balanced. Okay? That means the maximum friction limit is limit reached, that which is mu into n. Okay, that means uh no, it's like this: the block is tending to move but it's not moving. Okay,
okay,
no, there is one condition here: tendency to move. The block is tending to move but not moving. In that case, you don't use m into a because the block is not moving, there is no acceleration on it, right?
yeah. Let me see an example. Like
Yeah, yeah, you can send me. You can send me.
I think our time is done. I'm pretty sure.
Yeah, yeah, it's in between 10 to 12. So do you have exams for all this?
Yeah, we do. We have like midterms and they have a final. So the first three, I didn't really do well in one of the midterms because it was one of these. I was not very close, sure about how to do certain things. The first one went well, the third one went well, I think. Now I just have to do four and five well, and my grade should be like okay after.
Okay, when is your exam?
Well, the next one's in December.
Okay, okay, you have time, you can prepare.
Yeah, yeah, I have some time to prepare for the next one better than I
Okay,
did before. But it doesn't really necessarily have like I think we have three classes together, right? So this is the first two, and then there's one more.
there is one more. When is there one more?
No, I think I paid for three classes. I'm pretty sure. I also
Okay.
I sent the questions on homework on the WhatsApp.
One thing, one. Which question you were talking about? This only one question,
Yeah,
right?
yeah.
Yeah.
No, I sent a bunch, but in that there are
The
like
first
okay, for example, okay, not the third one, for example, you can see the third one.
you in you can see in this third one, you can see in this third one they say the block is moving up the plane with a velocity of 5.2 feet per second. Correct.
Yeah, yeah.
And
So in this
is it
case, will A
in
also
the
have a
no,
opposing force of MA? So
in
what
this
is
case
B?
you in this case you'll not consider this thing. What is this? Uh
The opposing
the,
MA, the other side. Like,
yeah, because it's moving up the plane with constant velocity. When the velocity is constant, where will not have acceleration. Correct.
oh yeah, yeah, that actually makes sense. Yep. So it'll just be zero.
Yes, that would be zero. That means forces are balanced. That's it.
Okay, okay, okay. But okay, okay. In question one, it says
When where is question one? Yeah. What is that? I need to find two blocks. Is it move? Like, do they
like
say?
how can you tell you need to use MA here because they don't talk about velocity anywhere in this case.
You can see the question they're asking for are acceleration. Then you need to include a, right?
Yeah, okay, yeah, they're asking, but like I'm just saying, if you just look at it, like in these homeworks, they make it a little bit easier for you to understand. But in the exam, they won't make it like this easy. They'll just show you a pulley like this, and they'll tell you
Yeah,
find the.
and see, that will be uh, actually it will accelerate. Okay, we will think that it's accelerate unless or until it's mentioned. Okay.
Mention. Okay, okay, fine,
Yeah,
fine, got it,
if
got it.
you know
Yeah,
in that question it's clearly saying that it's moving with a constant velocity, that's understood. If it's moving with a constant velocity, acceleration must be
Mhm.
zero. Suppose if they don't mention anything, we consider it to be accelerating. Okay.
Okay, and even for the
and we
third question now.
and
Okay,
we
sorry,
equate
go
it
ahead.
to and we equate it to m into a, the net force will be equated to m into a.
Okay, and if it's not accelerating, then it's just equal to zero.
Yeah, that's equal to zero.
Okay, and then imagine in the third question, now I know that I didn't ask this, but what if the velocity wasn't constant? Then
Yeah.
would there be a Newton, would this Newton's second law be on both object A and object B, or just object B?
See, so think that there is no constant velocity, all that thing is given. Okay, there is
If
no
there's
such thing.
acceleration is what I'm trying to say.
Yeah,
If
suppose
there is
if
acceleration.
and they must mention which way is it moving, is it moving up the plane or down the plane, that should be mentioned. Okay.
Okay.
Suppose think that if it's moving up the plane. Okay. Oh, sorry, it can't move up the plane. It only has to move down the plane, correct? There is no force acting here, correct?
Yeah, there's nothing pulling it up. Yep.
Yeah. Suppose it's think that it's moving down the plane with some acceleration a. Okay.
Okay.
And you can see I will have to write uh, the Newton's law for both. When you write the Newton's law, you should write for the combined A B system. Okay.
Okay.
Because the thing is, if you write only for either of the cases, either of the blocks, you'll also have to consider the tension while writing the Newton's law. Correct? That there is tension in the
Yeah,
string.
yeah, yeah. There
God,
is
God,
tension in the string,
God.
obviously. Yeah.
That you don't know. That you don't know, right? That is not given.
Yeah, but the tension's equivalent, so you can, if you equate it to tension on both strings, you can just equate it to each other and find something.
That
That's what
you can,
I did.
yeah. That you can find when the combined acceleration is known. It's like this.
Uh,
The
okay, okay.
progression goes like this. First, you'll have to find acceleration. With the help of combined acceleration, you can find the tension.
The tension, yeah.
Okay, it's not that you'll find tension and then you go for acceleration. Okay, first of all,
Okay, okay. Yeah, yeah, yeah.
first of all you'll be writing the Newton's law for the combined system. Then you'll get acceleration. Then you'll go for the individual blocks.
Okay, so my question is, if it's going down the ramp,
Yeah,
uh, and acceleration's acting opposite to B. So in this case, would both B and A experience the
yeah.
like
They will.
would
Yeah,
yeah, okay, okay.
no, the
Trying to
chord they will be moving with the same acceleration. Okay, because B is pulling, correct? B
Oh,
is
so
pulling.
just MA, so you can equate it
Just
to each other
MA. Yeah,
basically.
M, and that M will be MA plus MB.
Okay, 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 got it.
The no think that A and B is a combined system. Okay, that's it.
And that A is going to be A plus B, so it's MA plus MB. AB, sorry.
No. Acceleration won't be. You'll not have to add acceleration. They are moving with one common acceleration a.
Oh, sorry, yeah, yeah, okay, okay,
You don't
okay.
you'll
Yeah,
add
didn't
mass.
have to.
You'll not add accelerations. Okay, so
Yeah,
it's
okay,
like
understood, understood.
okay ma plus mb into a, that you'll find with the help of Newton's second law. and and what are all the forces acting, what are all the forces that is making the block move? There is gravity, correct?
There is
Gravity.
gravity, it's
Gravity.
frictionless, I think,
There
in
is
this
gravity.
case.
That means at since a is there is no friction between A and the plane, so there won't be any friction. But we have friction for B and A. That you will
Yeah,
find out. Okay, that will be
yeah, there is.
mu k into n. That all thing you know, right?
Yeah, yeah, I know that, I know that.
Yeah, so that's you find out.
And then, yeah, okay, okay, got it. Yep. So, okay, yeah, understood. So in these cases, both in the summations of x's and y's, it's all equal to zero. It's not equal to MBA or MA or whatever.
Yeah, in this case, it's not equal. It's equal to zero in this case because it say
Okay,
that
okay.
it's moving with some acceleration.
Okay,
One second,
understood.
one
Yeah.
second, one second, one second, one second, one second, one second. No, 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 no. No, 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 no. Even here, you'll have to consider M into A, because it's
Oh,
here they say, assuming that the blocks are given an initial velocity of 5.2 per second. That means it's initial. Afterwards, it may decrease. Okay, they're pushing the combined system with the
ah,
velocity of 5.2. Then, with the help of gravity, it may decrease, and with the friction being there and gravity is also pulling, it may decrease. They're giving just the initial velocity. Okay.
okay, okay. And the acceleration is in an angle, so so
Acceleration you'll have to find out with the help of second law. Okay.
okay. So the question is, if that because the acceleration is acting at an angle, they have to do it. Do you have to break the acceleration down the x and y components?
Where is acceleration acting at an angle?
Oh, never mind, never mind. Okay, never mind. I got my mistake. Never mind. I
Yeah.
got it. I got it.
No, it will be in one particular direction, right? Acceleration.
Yeah, acceleration will be in the x direction. If I take
Yeah.
the axis is based on the
Yeah.
acceleration acting at the x direction, the y direction the other way,
Yeah.
then
You
I
don't
can just I don't have to break it down.
you don't have to take x and y planes. You just take the plane as one axis. Okay.
Yeah, 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 I got it. I got it. Yep, you're good.
Then you'll only have one acceleration.
Okay, yeah, understood.
Yeah. That's
Yeah,
it.
that's about it. Yeah, and then okay, can I have or like it's fine. It's okay. It's not a big deal.
You can ask me. No, don't, no worries. You can ask.
Okay, okay. Just the fifth question.
The last one.
Uh, yeah, just the last one. This is just wanted a question.
Where is
In
fifth
this
one?
case,
I'm not getting. Where is fifth one?
there is oh sorry, fourth one. There's a fourth
Yeah.
one.
Yeah.
The last one, I mean.
Okay.
Yeah, in this case, you have to use the IMD, right? The impulse moment diagram.
Impulse moment diagram.
Yeah, like my professor calls it impulse moment diagram, where he like breaks down the forces, um, and then
Uh,
basically like the initial
Initial
um
momentum is equal to final momentum. That's what it is.
yeah, initial momentum plus I think I don't exactly know how I did this, but
Uh, I'll do one thing. I'll solve this and send you the solution.
yeah, that's all right. Yeah, that's okay.
Yeah.
That's okay.
So it's getting late. I have another class in 10 minutes. So
Yeah, yeah, it's all right, all right. So do you have one more class together?
maybe tomorrow we can do. Is okay.
Yeah, tomorrow's cool. Yeah,
Uh,
tomorrow's fine. Yeah.
you come up with all your doubts. We'll try to solve this. Okay.
Yeah, yeah, for sure. Thank you very much.
Thank you. Thank you. We'll meet tomorrow.
Thank you. Have a good day. Yeah, for sure. Yeah.
Bye.
Yes.